Hi, I'm Eric Steinbring at Hertzberg Astronomy and Astrophysics in Victoria, Canada. And hopefully in 5 minutes, I'm going to answer the question, if space-time is quantized at Planck scale, and so it jiggles their trajectories of photons from distant sources, can the quantum film be detected during their blurry images? You already have, I think, a introduction to this calculus, but it's been looked for 20 years. With Hubble, you can almost possibly see this. It would be micro arc seconds across in the optical near infrared. But that's roughly the size of the diffraction limit of the telescope. So it wasn't convincingly seen with quasars, which are good targets. They're fairly small and bright and distant. Better targets, the best target would be a gamma ray burst. And 20 years ago, roughly 2008, Fermi telescope was launched, which sees the whole sky and out to GeV, TeV level photons, so very high energies. And this sees gamma ray bursts, which are known to be physically small, less than a parsec across, and very bright. There are three measurements that it makes. One is whether it can see anything on the sky at all. And then when it does in its peripheral vision, it has to point the telescope at the source. That's called a roll angle. The second number is the error radius, so the patch within which it sees photons. And the third is its resolution limit, so the finest scale, the finest measurement that it can make for the direction on the sky of that source. There's three measurements it makes. And it's measured hundreds of those. And so the question is, what is the maximum blurring that the telescope should see, any telescope should see? And you may already have seen this too. This is corrected for the redshift of the source. So bluer photons, when they left the source at high redshift, are actually more strongly affected. So this is calculating what the absolute maximal effect is. But a real telescope only sees that blurring which is within its either its resolution or its field of view or the whole sky. And so that's what this calculation is doing. This is calculating for Hubble or for any other telescope farther off into X-rays and gamma rays, with based on what the field of view of the telescope is, what the size of the point spread function, how big the object should look on the detector. So that's what this is doing. And so providing that measure of the roll angle, the error radius, and the diffraction limit. And what comes out is the geometric mean of those things, we'll call that theta, is an important number. And the other thing it says is that this function turns over towards high energy. It flattens out towards the highest energies. And that's what this is showing. This plot is showing in a log plot what the PSF, the blue contours are what the point spread function of a telescope at high energy should be. If this off to the right is Hubble. This is the diffraction. The grayed out region is the diffraction limit of the Hubble telescope. And you can see we shouldn't have expected to see for alpha equals 2/3 much blurring. So that's what this line is the maximal effect at optical near infrared wavelengths, and then the blue off to the left is the PSF for Fermi. For example, the white curve is the roll angle expected off towards that direction in a high energy. This is the theta, so that mid-range measurement of the size of the PSF, and the black curve is the resolution limit, the sharpest images it could possibly make of a gamma ray burst. And thankfully, there was one in the last few years, which was the brightest ever seen. This is just lucky. This is GRB 221009A. Everybody saw this. Fermi for sure. It's the highest energy photons ever detected with Fermi. And this is what this red burst is what it saw with the LAT, with its imaging detector, degrees across. And that's expected. So the calculation that I showed, these are those blue contours again, this is a good fit. So actually all the data for all observations for Fermi are shown as outlines here, but I'll direct your attention to these triangles. These are the roll angle measurement for Fermi. This is the error radius expected for its X-ray telescope. This circle, all the other data points from other telescopes, similar telescopes. This is the resolution that it detected within the lat for GRB 221009A. And also Hubble looked at this, JWST looked at this, ground-based telescopes looked at this, and they shouldn't have expected to see a result for alpha equals 2/3 either. It's a great fit. I don't have time to go through every data point in here, but I'll direct your attention to where the highest energy photons that it detected, for example, in the halo. This suggests that these are all the GRB data forever taken with Fermi, is that it happens that that calculation of theta is a perfect fit for what the outer scale is of all gamma ray bursts, not just this one. This is the measurement taken with Fermi. We see it. So I direct you can look it up in this paper if you'd like to learn more about that. But the answer is yes. Blurring formulation favored by holographic quantum foam at alpha equal to 2/3 is consistent with the real PSF, the real measurement of the size of GRB 221009 and other GRBs. And that seems to suggest that blurring by the Planck scale is real. Thank you.